the post-lunch session on interactive proofs. So we'll have 4 talks during this session. All right. Are we all set? Okay, great. So our first talk will be on the Fiat-Shamir transformation of multi-round interactive proofs, and Thomas will be giving the talk.
Okay, thanks for the introduction. This is joint work with my co-authors Serge Veer and Michael Kloos. So the starting point of our work is an interactive proof, obviously, which is a protocol between a prover and a verifier. And the goal of this protocol is for the prover to prove knowledge of a witness, a secret witness, given a public statement X. So the prover knows the witness W corresponding to X, and the verifier only knows X. And the prover and verifier exchange a couple of messages. And in the end, the verifier decides whether to accept or reject the prover's claim. We will be restricting to public coin protocols, and public coin protocols, the verifier's messages, so the C1 up to C mu in this example, are chosen uniformly at random and are independent of the messages sent or communicated thus far. So interactive proofs have a number of desirable security properties, and we will be focusing on knowledge soundness. And informally, knowledge soundness states that a dishonest prover, so without knowledge of a secret witness W, should not be able to convince a verifier, or at least should only be able to convince a verifier at very small or even negligible probability. So that's the property that we will be focusing on. And examples of these multi-round interactive proofs were already given this morning by Nick. So you have a very large class of bulletproof-like protocols that all have these specific properties and that have become of interest quite recently, the last couple of years. So in practice, you want to deploy these interactive proofs in a non-interactive manner, and you can do this by using the well-known Fiat-Shamir transformation, where you replace the challenges sent by the verifier to the prover by random oracle queries. So instead of sending a message to the verifier and requesting a challenge in return, the prover makes a query to a random oracle and uses the output of this query as a challenge. So this is a very well-known transformation, and it sort of makes the protocol non-interactive because the prover does not have to verify or have to communicate with the verifier anymore to create the entire proof. So obviously, if you apply this Fiat-Shamir transformation, the cheating probability for dishonest provers increases. And the reason is actually that the dishonest prover in this non-interactive mode can query the random oracle many times. Many of these protocols, namely, have a cheating strategy that succeeds or that proceeds as follows. If the prover tries to guess the challenge before having seen it, before receiving it from the verifier, and if it guesses this challenge correctly, then a dishonest prover can succeed in convincing the verifier, even if it doesn't know a witness. So in the interactive setting, the prover has only one chance of guessing these challenges correctly, but in the non-interactive setting, the prover can just query the random oracle many times to try and cheat. And again, it's also quite easy to see that this cheating probability depends on the number of times the prover is allowed to query the random oracle, so the query complexity Q. So a very natural question to ask is, what is actually the security loss of this Fiat-Shamir transformation? So with what factor does the cheating probability, or more precisely the knowledge error of these proofs increase if you apply the Fiat-Shamir transformation and you go from interactive to non-interactive? So let us consider a very simple example. So suppose we have a 3-round protocol with cheating probability kappa. So this kappa is typically equal to the probability that the prover guesses the challenge correctly. And if you then apply the Fiat-Shamir transformation, it's quite easy to see that the cheating probability grows by approximately a factor Q, where Q is this query complexity, because the prover can simply try to guess the challenge Q times. So here we see a security loss of a factor Q, or at least linear in Q. So if we then look at this multi-round protocol, what we now do is we take the default sequential repetition of this 3-round protocol. Then we get a protocol with 2 T+1 rounds. So this is a multi-round protocol. And you can show that this protocol has, the interactive protocol has cheating probability kappa to the power T, because now if a prover wants to cheat, it must cheat in all these T instances. But if you then look at the Fiat-Shamir cheating probability, you see that it becomes Q to the power T times kappa to the power T, or at least approximately. And the reason is that also for the Fiat-Shamir transformation, the prover can simply attack all the T instances independently, so separately from each other. So what we see here is that we have a security loss that's exponential in the number of rounds. So in general, this is the case. So in general, the security loss of the Fiat-Shamir transformation is actually exponential in the number of rounds of the protocol. However, this is somewhat of a contrived example, because if you want to decrease the knowledge error of an interactive proof, you can also resort to parallel repetition instead of sequential repetition, and you don't have this blow up in the number of rounds. So it is somewhat of a contrived example, but it shows that in some settings the security loss is exponential in the number of rounds. So what do we know from prior work? So we have these forking lemmas. They have been known for quite some time already, and that show that the security loss for 3-round protocols is linear in Q. So what we saw in the first example for the 3-round protocol. And we also know that in general, the security loss is exponential in the number of rounds. And recently, we've seen some multi-round or some works on multi-round protocols, and they show that some of these multi-round protocols actually have a security loss that does not depend on the number of rounds. So we have these specific extractors, so straight line extraction, that uses a different technique. For the first one is for interactive oracle proofs, and the second one works only in the algebraic group model. So for a restricted class of protocols, we know that the security loss does not depend on the number of rounds. So what we do in this work is we show, first we give a positive result, where we show that if we look at these, a very broad class of interactive proofs, so K1 up to K mu out of N1 up to N mu special sound interactive proofs. So this morning, Nick also referred to these as these 3 special sound protocols. I'm not going to explain what that actually means, but this is a very large class of protocols. For example, bullet proofs admit this structure or have this property. But for these protocols, the security loss is linear in the query complexity Q, and it is independent of the number of rounds of these protocols. So the security loss is actually equal to Q plus 1. So that is the first result, is a positive result. Second, we also provide a negative result, which is actually, we show that there are also natural protocols or interactive proofs where we do see this exponential security loss. So it's not that we only see this exponential security loss for contrived examples. But to give some intuition on the results, I already said that knowledge soundness is the informal definition, or the intuition is that it states that dishonest provers do not succeed in convincing a verifier. More formally, knowledge soundness is defined in terms of a knowledge extractor. So an interactive proof is knowledge sound if there exists a knowledge extractor. And the knowledge extractor is basically given oracle access to the prover P star that is trying to attack a protocol, and its goal is to compute a witness or to extract a witness, a secret witness, out of this prover P star. And that, of course, it has to be efficient and succeed with large enough probabilities, with large enough probability. So what can the extractor do? In the interactive setting, the extractor actually plays the role of the verifier. So it can choose which challenges it sends to the prover, to the dishonest prover, and in that way it can create transcripts, protocol transcripts, and from these protocol transcripts the extractor can typically compute the witness. In a non-interactive setting, the situation is a little bit different. So where we look at these, when we look at these non-interactive random oracle proofs, such as the Fiat-Shamir transformations, then the extractor can answer the random oracle queries of the dishonest prover P star, and it may also reprogram the random oracle, basically meaning that it runs the prover again for the same random oracle, but it reprograms one of its entries. And the challenge here is that actually the extractor does not know which of these random oracle queries the prover P star is going to use. So in the interactive setting, the prover must answer or give a reply to the challenge that is provided by the verifier or the extractor. But in the random oracle setting, in a non-interactive setting, the prover can query many, make many random oracle queries and decide later which of those to use. So that's actually the challenge in the non-interactive setting. So what we do, very briefly, some ideas in our approach. We define an abstract sampling game that mimics the extractor for 3-round protocols. And a key observation is actually that reprogramming the random oracle for an input that is not queried by the prover P star does not change P star's output. So this seems like a very obvious observation, but it's actually crucial in the analysis. So what it basically means that if P star does not query a specific entry of the random oracle, then if the extractor reprograms that entry, then from the point of view of the prover P star, nothing has changed. So its output is actually going to be identical to the output before. So that's one of the observations that we make and that we incorporate into the analysis. And then another observation is that there exists a very natural recursive approach to go from 3-round interactive proofs to multi-round protocols. And what we do there is basically we have this 3-round extractor, and then this basically uses a sub-extractor instead of the prover P star as input. So I'm not going into details right now, but there is a very natural approach to do this. If you do this naively, you get an inefficient extractor, and to handle that, we introduce an early abort option. So basically, that allows you to make sure that the overall extractor is going to be efficient. So I realized I had to skip over a lot of the details, but I'm happy to take questions and also discuss them further later on.
Great. So we have a little bit of time for questions. So do we have any questions for Thomas?
So what's the exact running time of your extractor? You say it's still preliminary time, but there's all these abortion and
so
and
okay,
so
that's
do you have a concrete bound?
Yeah.
Or
yeah. So the exact running time of the extractor. So okay, let me see. So it's basically the product of all these KIs, because that's the size of the tree that you need to extract, times a Q plus 1. So yeah, we have a concrete bound on
it's
that.
not so bad. Okay.
Yeah.
Thanks.
Great. Additional questions? Yep.
So I would imagine your proof also would extend to this auxiliary input random oracle model with preprocessing. There is like a generic technique to do pre-sampling. Would it give tight bounds, or there is like a better way to extend your bounds to to auxiliary input random oracle?
I wouldn't know actually. So
Okay.
Yeah.
Great. Any additional questions? Otherwise, let's thank the speaker again. All right. So our next talk will be a virtual talk delivered over Zoom. So let's wait until we set that up. Okay. All right. Can you hear me?
Yes.
Okay, wonderful. So our next talk will be on steganography-free zero knowledge, and the talk will be given by Behzad Abdolmaleki.
Okay, thank you for the introduction. This is a joint work with Nils Fleischhacker, Vipul Goyal, Abhishek, and Giulio Malavolta. So in this talk, I'm gonna first start with the motivation. The motivation mainly say what is the definition of steganographic communications and what are the challenges so far in this area. And then we will list the result of the paper, and then we look at the new model, which is one of the results of this paper, to see how we can prevent this steganographic communications. And then we see how we can construct or instantiate an example for that. So Imagine that we have two parties, party A and party B. Party A wants to send some secret message to the party B in a way that the external observer should not be able to detect that. So this is called steganographic communication. So for that, one cannot use an encrypted channel. Why? Because this can be detected easily by the external observer. So one way that party A might be able to do that is to instead embed her message in any other message, like as in a photograph or other things. And also it is known that there is no way to prevent steganography communication in a plane model. So we have impossibility result for that in the plane model. And to overcome this impossibility, there are some directions that actually use that bring some constraints in order to overcome this impossibility result. For example, the first one is called collusion-free protocols, which actually tries to prevent a group of adversarial parties from colluding with each other by the assumptions that there is a physical sealed envelopes, and also plus some interactive pre-processing phase. And also another way to overcome to the impossibility and construct such a steganography-free communication is using synthesizations, which in this model, instead of using physical assumptions, here one consider an active mediator, which this active mediator sits between the parties, party A and B, and can modify the message. So it is an active mediator. But and also there are some other approaches which I'll not go through to that. For example, using trust setup stuff or other things. But all of these things, still there is a main question, or the main challenge is that, is there any more realistic model that can prevent this steganographic communications, not using, for example, some active mediator, because in the classical steganography communication, we want a passive external observer or a passive mediator. So the result of this paper try to somehow give a solution, another solution in this area. The first result actually is that we define a new model for steganography freeness, and then in order to instantiate it, we define a new primitives. We called it steganography free zero knowledge, or in short, it is SFZK. And then we construct SFZK arguments in two settings with black box simulations. In two settings, single execution setting, which means that one cannot use, which means that the pre-processing phase is not reusable, and multi-execution phase. And also, we give an impossibility result that this is the best case that one can get in this model. But in this talk, I only cover the first three parts, and the rest I will refer it in the full version of the paper. So here, a steganography, actually our model to prevent such a issue is divided in two phases. First phase is non-interactive pre-processing phase, which actually each party can send a single message to each other. And then this is an actual protocol which called execution phase. And in this model, we assume that only one party should be honest in the pre-processing phase, but in the execution, both can be malicious. And then we define steganography freeness in a following way. We say that, okay, an adversarial sender is given a beta B at the beginning of the execution phase. And then at the end, we ask and then we want that the probability that the receiver outputs the value, a bit B such that the execution transcript is accepted by the observer be negligible. And so now, before to instand it and construct such a primitives, we first quickly recall the key primitives that we will use in our construction, which the first one is zero knowledge with superpolynomial simulations. Here we assume that, I mean, for our construction, we assume that there is a 3-round public coin zero knowledge with the following properties, which is simulatable in the superpolynomial time. And also the second condition is that the first and the second message, since this is 3-round protocol, the first and the second message, let's call it alpha and beta, should be, for those, we have only one accepting cert message gamma. And also, if we fix the transcript alpha and beta and gamma, then either of the following should hold. This witness should be extractable, or there is at most one beta for the transcript alpha and beta and gamma, which is accepting. And also we need a special kind of NIV, non-interactive witness indistinguishability, which is called NIV with honest pre-processing, which is actually a NIV but divided in 2 steps, which in the first step, prover commits with some preliminary value, which in this step prover is not given any statement, and this is a statement independent. And in the second step, prover is given a witness and a statement to compute the real proof for the protocol. And we assume that the soundness hold as long as the first step is done honestly. And after that, now we can define the new primitives, which is called steganography zero knowledge. So here, to follow our model, which I was explaining here, we assume that this SFZK argument proceeds 2 phases. Again, non-interactive pre-processing, which each party just sent a single message, and also execution phase, that prover wants to prove the validity of some statement that is given in this phase. Execution phase, I mean. And now the security requirement is first the standard ZK scheme properties, which is called completeness, which says that for a valid prover, verifier should accept the proof. Soundness is it opposite for an invalid prover or invalid board. The verifier should reject the proof, and zero knowledge says that the proof of pi should not leak any information of the witness. And also we need to, and also we add 2 more extra properties. First is called observer soundness, which says that for any invalid word or for any invalid prover, no collision of prover and verifier should be accepted by the observer. And the last one is computationally unique transcript, says that for any valid word, 2 different set of efficient prover, P and B, and P star and B star, should not be able to generate 2 different transcript or 2 different proofs such that it is passed by the verification by the observer. So now let's see how we can instantiate it, how we can instantiate this SFZK. So there are some difficulties to achieve it, but the main one here is that if we want to get a black box simulation of the construction in a single execution, let's say, for the first, here, the normal way is that, okay, simulator works by the rewinding, which actually rewind the adversarial verifier in multiple times. So to do that, actually, this creates multiple protocol transcript in order to make the rewinding works. Which actually this is in the opposite of the new property computational unique transcript. Why? Because here simulator can be counted as an efficient algorithm. So this simulator also should not be able to produce multiple transcript. Otherwise, it will break the computational unique transcript property. So now one of the main challenge is that how we can achieve zero knowledge without violating CUT or vice versa. So to do that, actually, we extend the language in NIVI in the following, in the 3 branches. So with the first branch actually is gonna be passed, we will see, by the prover. And the second branch will be used by the simulator in order to simulate the proof. And the last branch, which I will not talk about it in this talk, this is only will be used in the proof in order to prove the indistinguishability between the first 2 branches. So now, as I mentioned, the protocol, this SFZK has 2 phases, pre-processing phase and execution phase. In the pre-processing phase, prover commits to some messages 0 and some randomness R primes, and then generate the first message of the HPP NIVI and the first message of SPSCK. That later it will be used to prove that, okay, the first message of HPP NIVI is generated correctly. And then transfer or make the green one actually public. And on the other side also, verifier first generate a random image of Y from some one-way function, which is supposed to be exponentially hard. And also sample some instance X prime from some average case hard language, hard relation R with unique witness W prime. And also commit in the second message of a beta that will be sent for the SPSCK, because we assume that this is 3 rounds, as I mentioned in the preliminary. Now in the execution phase, prover first commit to some messages 0 by using the random coin R prime, which already fixed in the pre-processing phase. And after getting the decommitment values from the verifier, which contains the beta and some unique witness W prime, which verifier already committed in the pre-processing phase. First, prover checks the validity of those, and after that, create the second message of SPSCK and the NIVI part, which the second message of SPSCK says that, okay, the first message of the NIVI is well formed, and the NIVI part wants to prove the first branch of the protocol. So here, and then in order to simulate and to simulate the protocol, now instead of using the normal rewinding, here the simulator first compute the first commit to some message 0, and after getting the decommitment message from the verifier, which is beta and the witness W prime, then he again rewinds the verifier and then start from the beginning, and instead of commitment to the 0, he commits to the witness W prime because he already got it from the verifier, and then can pass the second part of the, and then generate the NIVI and SPS for the second part of the, for the second branch of the language. So, okay, now, as a summary, we will be, I was just talking about the new model and how we can implement it in the single execution setting. And the rest of the result, I will refer to the paper, and as a also open problem that might be interesting to somehow look at this property. I mean, steganography free in the multi-party setting or some other models as well. Okay, thank you.
Great. So we have time for one quick question if anyone wants to ask while the next speaker starts setting up. So I have one brief question. So in your construction, you rely extensively on sub-exponential hardness. Can you comment on whether it might be possible to build steganography-free zero knowledge using polynomial hard assumptions?
Well, that's a good question. I would say using this sub-exponential hard assumption actually is a main trick that we can get rid of. I would say I don't know how to construct it, because there are some difficulty, you know, if we want to use the poly in the proof, which which I'm not sure that one can explain it in this short time. Yeah, but I have no idea that how it would be, because yeah.
Sounds good. Great. Let's thank the speaker again.
Yeah, thanks.
Okay, are we good? Don't press this last one. Okay. All right, so our third talk for this session will be on vector commitments over rings and compressed sigma protocols, and Ignacio will be giving a talk.
Thank you. Yeah, this is a paper with Thomas, Ronald Kramer, Ivan Damgaard, and Daniel Escudero. And this is about generalizing the theory of compressed sigma protocol, which was introduced by Thomas and Ronald in Kyoto 2020 to proving like statements, linear forms for committed values over rings. So first of all, let me remind you, even though all of you will probably know what the commitment scheme is. It's usually described as the digital equivalent of a safe box, where Alice can put a message in this box by applying some function, some randomized function, and then she can open later the box to reveal the value that she put in. And the properties that we want is that basically Alice can, once she has put the message in the box, she cannot open it to two different values, and also that when the message is in the box, but before opening, nobody else can learn anything about the message. Then what we will want to construct is homomorphic commitments, and homomorphic commitments, we describe them as follows. So the message space is going to be a group that we write additively, and then the commitment space is some other group, multiplicative group. And then what we want is that if we multiply two commitments to X and Y, then the resulting thing is a commitment to X plus Y. So pictorially, you have there the commitments to X and Y, then you multiply them, and then you get some commitments to X plus Y with some randomness that depends on the randomness and messages that we have originally. But I guess that the important thing here is that the opening a sum of messages should only reveal the value, the sum of the messages, but not more information about the individual messages. So this is maybe the important thing about the homomorphic properties of the commitment. Then we have the notion of vector commitment. Basically, when you consider the binding, hiding, and homomorphic properties, you could just think of that to be a commitment on a certain group that is the direct product of n copies of the same of some other group. So you are committing to vectors of elements. But when we talk about vector commitments, we also want some additional properties, namely, we want to have a commitment that is succinct. So basically, it should not grow too much with the length of the message that we commit to. And then we also want that we want to maybe open positions of the vector, like coordinates, individual coordinates of the vector, also in a succinct way. And for us, that will be like polylog n. That's what we will get. So in particular, this position opening is just a special case of what we could call linear opening, or opening of an inner product with a known public vector. So basically, like having some kind of non-interactive proof for a relation that's well, given some commitment and some value. We know a vector that commits to that commitment and satisfies that certain linear, public linear form applied to the vector gives you the value y. Now, this is a more general case than position opening, because you can just have a position opening by just setting this form L to be the form that gives you like the ith coordinates for whatever ith position you want to open. Okay, so this is the definitions I needed to like state our result. That is that we construct vector commitments for vectors over the ring of integers modulo m for any m that is not necessarily prime. And this is like the sort of novelty that our commitments will be also homomorphic with respect to the group of integers modulo m, and this m doesn't need to be prime. Now these commitments that we construct have in fact constant size. They don't depend on the length of the vector. We also construct then compressing map protocols that prove statements of the form that I just explained in the previous slide. And these proofs in our case will have log n log n size. So that means that in particular, for example, our commitments can or have this or log n size position opening, but we can also like open more general combinations of the coordinates of the vector. And in fact, it's a bit better because we can even like amortize this. So this complexity there is like for opening one or proving a statement over one vector. But in fact, we can prove the same sort of form for like these statements with the same complexity. So this is somehow like batched or amortized. Yeah, so now for the rest of the talk, let me give some details. The first thing is that we construct is this vector commitments for rings modulo m, for not necessarily prime m. And one problem here is that, well, as far as we know, we didn't find like any construction out there that was homomorphic for like these rings. So generally, because for example, Pedersen's commitment work, but only for, say, for example, prime values of m, because they need to work in a group that's where the discrete log is hard. So if and this group has to have order m. So in particular, if m is 2 to the k, then you are not going to get that. Another possibility could be to use Damgård-Fujisaki construction that is in homomorphic vector commitment for integers. But the problem there is that if you like open a sum of vectors, then you are revealing the sum over the integers, and that gives more information than revealing the sum modulo m. So our constructions for these vector commitments have basically two steps. One is to construct actually the homomorphic commitments for single values and single value, and then we can have, or we find a general generic construction of vector commitments from single valid commitments. So the second thing, let me explain the second thing first. So if you have a commitment for single values, we can construct a commitment to vectors quite easily by just taking the same setup, but now sampling with the single value commitment, sampling basically commitments to n random values. And then in order to commit to a vector x, we just take these values that have been sampled in the setup, we raise them to the coordinates of x, we multiply them, and then we multiply by a commitment of 0 with a single value commitment. And this simply works. Now let me just show you how to construct the single value commitments. And here we have constructions based on factoring assumptions. And we separate the cases that m is odd and m is even. So for m odd, we have this construction here. Now the setup actually, if you realize, it's just outputting a random element in set m star, completely random. I mean, I just wrote it there to notice that that's any element that you sample there is of the form a to the m for some random a. And then once you have sampled that in the setup, then it can because the commitment can be constructed by just raising these elements to X and then multiplying by R to the N. And that works. Of course, always to guarantee bindingness, the committer should not know this value A in the setup. Then for M even, we have the problem that M is not co-prime with phi of N. And then in that case, we have to adapt the construction a bit, and then we work over the group of elements with Jacobi symbol 1, and the commitment has to be adapted a bit. So we have to add this element -1 to the B. But this simply is very similar to the other construction. Okay, so that was the commitments, and now to show you a little bit how the opening, the linear openings work. Basically, we are, as I said, generalizing this compressed sigma protocol theory. So first of all, we can assume that the modulus M is power of a prime, because otherwise we can use the Chinese remainder theorem and reduce to that case. So assuming that M is of this form, now if M was prime, one could just use or define a standard, quite standard sigma protocol with soundness 1 over M in this way, and then use this theory of compressed sigma protocols, where you are basically like compressing the last step of this sigma protocol, having or leading to a shorter proof. While at the same time, well, you are losing a little bit of soundness, but not that much. The soundness of this compression step is 2 over M, important, and then soundness that you get in the end is 2 log M over M. But now the problem is that if we are over rings where M is not prime, M is a power of a prime. The problem is that in general, this construction requires that the challenges that the verifier sends live in a space where the difference of 2 different challenges needs to be invertible. And the soundness is given by the inverse of the size of that set. And also the compressing is also given by the soundness of the compressing step is 2 over that size. So when we are when we are in the case where M is 2 to the K, for example, then the sets where we have the difference to be invertible of any 2 elements can have size 2 at most, because we cannot have 2 elements of the same parity. That means that the soundness would be 1/2 of just of the sigma protocol that you have in the beginning, but even it is even worse when you compress, because then you don't even have any soundness there. So instead, we use Galois rings, which is a tool that has been used in a number of works in MPC over rings. And this is an extension of the ring of integers modulo p to the k, where essentially you are taking like a larger ring that has like a exceptional sets, so sets where the differences are of any 2 elements are invertible, which are larger, and then you can get as large as you want by increasing the degree of the polynomial that defines this Galois ring, and then you get p to the d. And then the question is, okay, then you have to commit to vectors that have like elements in that extension ring. But the point is that you can always see those commitments or those vectors as d vectors over the smaller ring. So basically, a commitment to that is just the commitments to vectors over the ring, and then everything works fine with the homomorphic properties. And in the end, we get a protocol that actually can prove these statements of that form, because of this sort of like larger ring that we are taking. We can batch these statements, and we have the complexity there that I was like announcing at the beginning. Right, so in particular, we have position opening of this complexity, log n log n. And well, I have left some things without mentioning, but basically we have in the paper, we have constructions of single valued commitments from what we call commitment friendly groups, which is an abstraction of or a generalization of what we have, of what I have explained. And we have also constructions on class groups that that help with like the trustedness of the setup, more details and comparisons with the Sigma protocols, and then an application that sort of motivated a little bit us at the beginning, that is to verify all computation on encrypted data in a paper in PKC 21, where it's like working over rings has certain advantages instead as opposed to working over rings. So yeah, that was all.
Great. So maybe we have time for one quick question while the next speaker sets up. So can you comment on whether you can extend beyond linear functions? So say I want to, can you say anything about extending to proving nonlinear relations, such as quadratic relations or higher degree?
Yeah, so we haven't looked at into that, but I suppose that I mean, in the compressed Sigma protocol paper, they have certain techniques to address that with like encoding things with sort of polynomials, like a kind of Shamisi in some way. So I suppose that we can do that in this case, but I haven't. We haven't looked at that specifically. So
Great. So let's thank the speaker again. All right, so our final talk for this session will be on universally composable Sigma protocols in the global random oracle model, and Leah will be giving the talk.
Hi, I'm Leah Namisa Rosenblum. I'm here to talk about universally composable Sigma protocols in the global random oracle model. This is joint work with Annalise Sanskaya. The point of this work is to create better non-interactive zero-knowledge proofs of knowledge, or NIZICs for short. Typically, NIZICs are constructed from Sigma protocols that are made efficient and non-interactive using the Fiat-Shamir heuristic in the random oracle model, or ROM. Most applications of NIZICs use them as follows. Alice has a value v. She wants to convince Bob that this value is correct. So she generates a proof pi that v is correct and sends v and pi to Bob. Bob then checks the proof. If the proof is valid, Bob accepts v, otherwise Bob rejects. And this appears in countless cryptographic protocol designs. The pros of this are that the Fiat-Shamir transform is very efficient, and the NIZICs are provably secure in the random oracle model as long as they are by themselves. The caveat being that if they are not, security is not guaranteed when the NIZICs are composed, as in many of the applications given. And composable security is non-trivial. So recently works have shown that there are practical attacks on the non-composability of these NIZICs that lead to malicious provers being able to forge proofs. So we would want a universally composable, or UC version of NIZICs that maintain reasonable efficiency in the random oracle model. In this work, we define NIZICs in a more composition-friendly way. We then use our definition to identify standard security properties that are both necessary and sufficient for obtaining UC NIZICs in the global random oracle model, where the global random oracle model is a more realistic model where all the parties across all different composed protocols share the same random oracle. Finally, we realize efficient UC NIZICs in the global ROM using the randomized Fischlin transform. So the implications of our work are plug and play NIZICs for any application that maintain efficiency in the ROM. I'll begin the technical details of the talk with the ideal functionality of these NIZICs. So in the UC model, the ideal functionality is the party responsible for forming the output of the honest parties, in our case, proofs and verifications of proofs. FNIZIC has three interfaces: setup, prove, and verify. In the setup phase, the honest party sends a setup request to the ideal functionality, who passes this request to the ideal adversary, which is the entity in charge of helping the ideal functionality form the output for the provers. So in the prove phase, the honest party induced by the adversarial environment to prove a statement X with a witness W passes this to the ideal functionality, who either produces a proof or it outputs fail, computed as follows. First, the ideal functionality throws out the witness and computes the proof according to the simulate algorithm. If the verification of this proof fails, then the ideal functionality outputs fail. Otherwise, it outputs the proof. In the verify phase, the honest party sends a proof for fnisic to verify, and fnisic either sends the verification or outputs fail, again computed as follows. If this proof is valid and not simulated, then fnisic computes the witness according to the extract algorithm. If it is able to extract a valid witness, it just outputs the verification, otherwise it fails. We want to show we can realize this functionality in the global random oracle. So now we'll talk about global random oracle. The first is a strict setup that functions very closely to a regular random oracle, where Alice sends her input X, the oracle has some random function, and it returns the value of that function computed on Alice's input. Unfortunately, it's not possible to achieve SNISX in this setting because typically the simulator needs to be able to program the random oracle in order to simulate proofs of statements without a witness, and it needs to see the adversary's oracle queries in order to extract witnesses from the adversary's proofs. So we build those functionalities into the global random oracle as follows. First, the observability interface. The oracle now has a mouth from which it's going to blab all of the illegitimate queries, which I will explain in a moment. The interface works similarly, except now Alice has a session ID, which she sends with her query. If that session ID she sends with the query does not match her actual session ID, then the oracle adds this to the list of illegitimate queries for her session. And now Alice can query for illegitimate queries and see that list of illegitimate queries. This allows the extractor to observe this list. And in the in the UC model, the environment is not part of any legitimate protocol session by definition. So this will allow the extractor to extract the queries from the environment's proofs. Extract the witness. Next, we add the programming interface, which is in the form of a little imp under the table who's going to program the output values of the random oracle. So Alice can now send a programming request. Because this is global, we have to let anybody program the random oracle. And so as long as that index has not been queried yet, the imp programs the oracle. But because if we don't want to allow Alice to cheat. If Alice is an adversary, we don't want to allow her to just program the oracle and forge proofs. So we add an interface called the isProgrammed interface that allows anyone to check whether indices in their session have been programmed before. So if Alice's session ID that she sends with her query matches her actual session ID, then the random oracle reveals the programming. Otherwise, it does not. Again, this would allow the simulator to program, but because the environment is not part of any legitimate protocol session, then the environment cannot tell whether the simulator has programmed the random oracle or not. We're working in the UC model. So very briefly, there is a real world where the parties are running the real cryptographic protocol Pi, and in the presence of an adversary A. In the ideal world, there are dummy parties who are talking to the ideal functionality F in the presence of an ideal adversary S, and we say that Pi UC realizes F if no environment Z can tell whether it is living in the real world or in the ideal world. Our first result says that any protocol that realizes fnisic in any global random oracle model must have three properties. First, it must be overwhelmingly complete. It must have the non-interactive multiple special honest verifier zero knowledge or NIM-Schwizik property. And it must be non-interactive special simulation sound or NIS. So the overwhelming completeness property says that given any honestly computed proof for X that is in the language of R, the probability that the verifier accepts is overwhelming in the security parameter. The NIM-Schwizik property says that polynomially many proofs from the simulator are indistinguishable from polynomially many proofs from the regular prover. And the NIS property says that given any valid and non-simulated proof, the extract algorithm must be able to extract a witness from the proof using only the adversary's queries to the random oracle. And this must hold even when the adversary gets to see polynomially many proofs from the simulator. Okay, so these properties are necessary to achieve UC NISX, and how do we actually realize them? using something called a straight line compiler. So this will allow us to get those properties. A straight line compiler takes any Sigma protocol as input and produces a tuple of algorithms with the following properties. The setup, prove, and verify algorithms all have access to the random oracle, and we define it to have these three properties just discussed. There is a straight line compiler already in existence, namely the randomized Fischlin transform. So in the full version of his paper in 2005, Fischlin showed that these three properties hold for the original version of the Fischlin transform. There's an updated randomized version that Kondi and Shalat show slightly different versions of these properties. So we just update to show that the randomized Fischlin transform also has these three properties. And we show that these three properties are sufficient to attain UC-NIZX in the programmable global random oracle model. So as long as you can program the global random oracle, you can take any Sigma protocol, run it through a straight line compiler, and obtain UC-NIZX. And the proof works briefly as follows. We just replace the honest party there slowly with a dummy. So we start in the real world, we replace the prover with the simulator, reduce it to the NIM-Schwizik property, then replace the verifier with the extractor, reduce it to the NIST property, and now we've replaced all of the entities, and this looks like a lot like FNIZC and S. So we just rearrange the components. This assumes this little imp down here is programming the random oracle based on the localized session of each party. So if you don't like this assumption, we have an additional construction that works without this, the programming interface using a CRS. So the prover will show that either they have a valid witness to the proof or they have a trapdoor to the CRS. So in the real world, the provers can compute this CRS for a one-time setup cost using a UC non-interactive secure computation protocol and only the observable random oracle. And in the ideal world, the simulator can generate the CRS with a trapdoor. So given this OR protocol construction over R or the CRS relation S, the restricted observable global ROs, this is the non-programming random oracle, you can take that OR protocol and run it through any straight line compiler, and you will end up with a UC-NIZC in the observable only CRS hybrid model. The proof is similar to the last proof in spirit. We don't have time to go through it, but it follows very similarly. And thank you.
Great. We have time for questions. So, yeah.
Yeah, so apologies if this is a silly question. I'm not familiar with the sort of UC-NIZX stuff, but what goes wrong with the Fiat-Shamir transform for building NIZX in this like global programmable model?
Yes, so the source of the attacks with composability are, the root of that is with rewinding. So a lot of those attacks, and I refer you to the attacks listed, I guess, on the first slide, but because you rewind it as you start to compose the protocols, it kind of blows up the reduction size, and it turns out that leads to the ability to kind of forge one more on top of the proofs that were given. So yeah.
Thank you.
Yeah.
Great. Additional questions? Yeah, in the front and on the side.
So just one quick question about the CRS. So if you could elaborate more on specific, like the CRS needs to be local for each execution of the protocol, or okay?
That's correct. It's a session local CRS. Yes. So it's not quite global. That aspect of it, it is a session local CRS. However, the parties can compute it using only the observable random oracle in the beginning of the protocol session.
All right. And one final question, I think.
I think you answered the question, but yeah, just I would like more detail on how you do this pre-processing phase, like to generate the CRS, like how many, you said it's non-interactive, like non-interactive, I suppose you mean like 2 rounds, like?
Yeah, great question. So the reason why we did the proof, or that I formulated this kind of in the observable CRS hybrid model, is because technically you would add the interaction at the beginning of computing the CRS. So that is an additional round. So assuming that you have that CRS at the beginning of the session, then from that beginning step on, everything is non-interactive. So you could rephrase the theorem statement 3 as being just the GRO, like just the observable hybrid model but then you would be assuming kind of an additional interaction step at the beginning to compute that CRS. No, so the beginning round kind of, it's a one-time setup cost. So once you compute that CRS, everything is just like non-interactive as normal.
So how many rounds do you require to generate the setup?
It's a non-interactive.
So just one round that
Correct.
goes from prover to like, that's what I.
Yeah, so it's a paper, it's Canetti et al. 2014. It's the UC NISC protocol in their paper. It's NISC, so it would just be adding one additional round. And for details, I'll refer you
Right,
to this.
sure. Thank you.
Yeah.
Great. So let's thank the speaker again. And this concludes the session. And I think we have a half-hour coffee break. We'll reconvene at 3 p.m.